Um, Miranda, are you still here? So none of you guys know. Well, the online guys did not notice that I muted. Um, so Limbo, are you here?
Yes, teacher.
So so
Question?
you didn't so you didn't notice I muted? I was muted.
Yes, you have no once the second class start, but I don't know if my device is right working, so I
Okay.
didn't tell you.
Okay. Yeah. So
But
next
now
time
I
if
can
you
hear you.
yeah next time if you can't hear, just just let me know.
Okay.
So now like we have this 2D convolution, so we are just sliding through this again, but instead of generating this this 1D shape, uh, the convolution the convolution is going to sliding through this two dimension. So how it works is that the filter is going to sliding through first like row wise, and then starting the second row, and then starting the third row, right? So in this way, the output is also going to be a cube. And it did not finish this whole convolution process, but you have a couple of more layers to do the convolution. Does that make sense? Does that make sense? So well, so for this convolution, it's a little bit simplified because we did not, talk about the padding and the padding, the stride and all that. So the padding means is that, so for example, like, if without the padding, if you do this convolution over the green filter, or is the green the no the green actually is the output. The green is actually the output. If you do the convolution over with the blue one, so the output is definitely going to be smaller than the input dimension, right? Because the filter has a size. And for example, let's say like this is a 3 by 3 filter, and let's look at the blue input here. The blue input is the 5 by 5, right? So without padding, what will be the size of the output? Without the padding, what will be the size for the output feature map? So let's see, like without padding. So the 3 by 3 filter is going to start from here, right? 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 So that's going to be one item. And then you're sliding through and you're sliding through. So for each row, how many items are you going to have? Three, right? So each row you have three. And then like for each column, how many items are you going to have? So let's see. So you slide through this first 3 by 3 blue cube, and then you come down here, and then you come down here, right? So how many items for each column you're gonna have? Three as well. So for a 5 by 5 input feature map with a 3 by 3 filter, you are going to have a 3 by 3 output feature. Does that make sense? So that's, so if you are keep doing this, you are going to have a smaller and smaller feature map until it's reduced to one, right? So that's probably not what we want. So one way to fix this is do this padding. So instead of like, just doing this on this input feature map, we are padding this whole input with all these zeros. Okay. You can see that like we have. So by doing the padding over here, we can make sure the output feature map size dimension is the same as the input feature map. Does that make sense? So there are different ways of doing the padding. This is called zero padding. This is called reflection padding. What that is that while the 95159, so like a Sudoku thing, right? So you have 5915. So it's a reflecting like a mirror to reflect the value from the original matrix. Also, we have this replication padding. So we're just repeating, the number on this cell. Okay, so in a lot of like tools like PyTorch, by default is doing the zero padding. Okay. In convolution layer, a very important concept is this receptive field. What does that mean? And understanding receptive field actually is very important in understanding what does the convolution actually does. So if you look at this, what it says like in convolution, each output elements depending on kernel H and the kernel width, the kernel height and the kernel width receptive field in the input. So each successive convolution adds k minus 1 to the receptive field size. What does that mean? So let's say like if this is the layer 1, okay? Let's assume this is layer 1. And we have the 3x3 filter. And when you are using a 3x3 filter to convolute with this input, and you got one output for here, right? Now, the question is, this one cell over here, the output from this convolution output, for this output, the information you have from the original input is only 3x3, right? Because you are pretty much just processing that 3x3 information to get this output. For whatever kind of information you are extracting, like usually the convolution, the filter, what it does is that filtering all these different frequency of information in this image. Or for example, some of the filters are going to capture the edge of the shape, like the dog shape, like the edge of the shape. That's some of the convolution that does. So if that's the purpose of this filter, then for this information you're extracting, you are essentially only extracting the edge information from this small, just a subset of the original image. Does that make sense? Okay. Now, if you are looking at this input, then it's extracting the information from this small piece, right? Right. And then we have the second layer of this feature map. But remember, in this feature map, each cell only has the information of a 3x3. For whatever decision we are making, for example, I want to do segmentation, or I want to do a classification. Each cell only has the information for that small window. Make sense? But now here's the magic. When we are connecting multiple convolutional layers together, let's come to here. So when you are, for this green window here, again, we are going to have a 3x3 filter for this green window. 1, 2, 3, 1, 2, 3, 1, 2, 3. You get this one output here. Okay. Now think about, for this green cell, how many cells of information it's extracting information from the original image? Is my question clear? So this image only extracts information from this 3x3. But what about this green? Related to the original image, this green has information from how much of the original image? Okay. 5 by 5? How do you come up with 5 by 5? So tell me, which 5 did you get information from?
Be the original. Well, maybe I'm not thinking about it right.
So
maybe it's bigger. Is it 9 by 9? Or am I that good?
So who can walk me through like your logic? Like how do you get? So for this green cell, how many cells like information I can get from the original image? Yes.
Just 9 cells, so 3 by 3. Because you're still shrinking 3 by 3 into 1, and then that's distilling into that 1.
So it's a 3 by 3, still even related to the original image?
For one of the green cells?
Yes, for one of the green cell over here.
I think so.
Okay, that's one answer. Alex?
It's the 5 by 5 top left.
It's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 by 5. Why is that?
Because the convolution of I'm just gonna say the corners of the green one.
So this is, let's say this is a teal, okay? So this is a green. Okay. So this green cell over here, it gets information from this green, this is 3 by 3 green window, right? Right? But if you think about this teal cell gets from this 3 by 3, right? What about the second cell in the green window? This one gets information from where? This one. The second cell in this green window gets information from this 3, right? This 3 by 3, right? Does that make sense? What about this one? This one gets information from this 3 by 3. Does that make sense? Does that make sense? So this green window actually, well, this green window over here together gets information from this 5 by 5 from the original image. And now this little green information, this little green cell over here essentially gets all this information extracted from this 5 by 5 window in the original image. Does that make sense? So by concatenating all these convolutional layers together, essentially each layer more, we are increasing the receptive field. Does that make sense? And that's how the latter layers, eventually the latter layers is going to get the information from the whole image. And that's how it helps you to make the decision for the whole image, not just, focusing on a small part of the image. Yes.
Can you reduce the number of layers by having a bigger kernel with different weighting to kind of like approximate that or not?
Well, you can. So if you can have a bigger, so it's about the width and the depth of the network trade-off. You can, but I don't know the expressive power, like how much information you can capture for this kind of two different design. There are a lot of later we are going to talk about this neural architecture search. Essentially, basically, we are going to ask an algorithm to compare, like I have a bigger but shallower layer, or have a small kernel but have a deeper layer. Which one gives you the best accuracy for the data set? So stay tuned for that. Yeah, but that's kind of the idea. So by doing this, you start to increase the receptive field to focus on the whole image, kind of like the higher level of information. Make sense? So that's the power. That's the key idea behind this convolutional layers. Okay. And that's why it says, well, each successive convolution adds k-1 to the receptive field size. So each more layer, basically, you're expanding how much window you are looking at original image. Make sense? Good? All good? Yes. Then with L layer, the receptive field size is L times k-1 plus 1. You can easily get that number. So problem, for larger images, we need many layers for each output to see the whole image. And the solution downsample inside the neural network. And that's what we are going to talk about later, this downsampling. But before talk about that, we also have this so-called like grouped convolutional layer. What that means is that, well, so far for all these channels are going to calculate with all these weights to get to the output channel, right? So the grouped convolution basically says, I'm going to group the weights into two different groups. And for this yellow group and this green group, the yellow group is only going to focusing on the first half of the channels. So I'm no longer going to aggregate the information across the whole channel, all the channels. I'm going to only aggregate information over half of the channel, and the green is over the other half of the channel. So apparently the goal is that, so now like by doing this, we are cutting the computation need. Because originally this part, this yellow part, not just need to aggregate this part, but also need to aggregate the second half, right? And the same for the green one. So now we're kind of like cutting the computation by doing the grouping. If you are doing the grouping to the extreme, this is a depth-wise convolutional layer. What it means is that now essentially I'm going to have one. I'm going to have the weight for each channel. So here you can see that. Oh, while this weight matrix is going to aggregate over all the channels. Now this part of the weight only going to aggregate over half of the channels. Now, if you do the extreme, then this weight is only going to aggregate over this one single channel. Does that make sense? So that's called depth-wise convolutional layer. And apparently this also reduces the computation because now this weight only need to do the convolution for this particular channel and don't need to do the computation with all the other channels at all. Okay, so this is all like these design trade-offs. And of course, this reduces the computation need, but also like will reduce the power of the network. And it's all about how much sacrifice you want to make to kind of like to gain the efficiency improvement. And then we have this pooling or downsampling step. So what that does is that like we already talked about this, like, you know, for large image, we need many layers for each output to see the whole image. So one fix to that is that for each feature map, we are going to shrink it. So instead of looking at when you are shrinking the image, what that means is that you are looking at a pixelated image, right? So like Minecraft, you have this pixelated image cell. So what it does is that, but you have fewer of data to look at. For example, for this original image, let's look at this one. Say this is the original image. There are different ways of doing pooling. So pooling or downsampling. So this max pooling basically says, oh, I have this blue 4 cells, okay? I'm just going to get the biggest number in these 4 cells, which is 5. Now that's only 5 left. For this yellow cell, the maximum number of 7, then I'm going to have 7. So 8 and the 3. So now from this image, you get this image. And when you are doing this, you are going to start to see like pixelated images. Well, but of course, like when we are looking at the feature map, kind of pixelated feature map, we can't really visualize this, but that's kind of the way to understand this. Okay. Or another way of doing this downsampling is this average pooling. So instead of just using the largest number in this group, we're just averaging them. So 5 plus 2 plus 1, which is 8. 8 divided by 4 give you 2. Okay, so by doing this, you are kind of see this. So we know that when you are pixelating the image, you can still see the shape, just not like clearly, right? Normalization. Normalization is one of the harder concept to understand. So what a normalization is that a normalization layer is you have all these input features to the layer, and the normalization layer is trying to constrain the input to a certain distribution. So we know that when you feed a bunch of data to this layer, to this whatever layer, it's a bunch of data, and all this data has a distribution, right? If you flat them into just a 1D array and you draw them on this 2D dimension, they have a distribution. Does that make sense? And what it does is that it calculates the mean, which is the mu I, and it calculates the delta, which is the standard deviation over a set of pixels. Okay, and then like for original xi, for whatever xi it is, it's going to use this formulation to get the xi hat. By doing this, we are making sure the mean of this new data set, this transformation from xi to this xi hat. Let me see, how can I visualize this for you guys? Okay, let me try to visualize this for you guys. So let's say this is a 2D dimension plane, and we have like a bunch of data across, scattered across this. And now I'm just using a 2D points to visualize because it's just easier to visualize. So let's say I have a bunch of data just scattered through this 2D panel. Okay, and apparently they have this distribution on x-axis and the y-axis, right? And like if you look at this image, usually they have a center and they have a kind of like distribution. Some of the points are away from the center, some of the points are closer to the center. So that's the distribution of all these points. Make sense? Make sense? Now, what we are doing with this normalization is that we are trying to bring this back to the center of the to the coordination. Okay, and also we are going to, for example, for this distribution, the variance is kind of big. Some of them are away from the center, some of them are close to the center. Now we are doing, by doing this, we are making sure all these points are constrained into this kind of distribution. So for example, the far points, we are going to pull it back to here. And also we are going to move the center of all these points to here. Does that make sense? So in this way, we are redistribute these points while still maintaining some of the characteristics. All good so far? Why we are even doing this? The reason is that it's good for training. So by constraining the distribution of all these inputs to each layer, when you are training this network, again, like you don't need to fully understand for now. We are going to talk about that when we are talking about the training of the network. By constraining all these points, so the training is going to be much stable. It's going to converge much faster. Okay, and then like you may have a question, say, oh, if you are doing the normalization, the output is no longer the actual output from the previous layer, because you already shifted the whole thing about all these points, right? How does that affect the accuracy of the network? So the key trick is that you are going to have two trainable parameters, trainable the scale and the shift. Okay, so the scale is basically multiplied with the scale is multiplied with x hat plus the shift, and these two parameters are trained during the training. The key idea is that, well, if the original distribution is really important to the accuracy of the output of the network, you are going to learn these two parameters to shift the distribution back to the original distribution. But if the distribution is not important for the eventual task, then this kind of normalization is to help me to speed up this whole training process. So that's kind of the key trick. You just need to have a rough idea, know what the normalization is. So by doing this, and then we can do normalization over a bunch of data. We can do I think the most thing that we've heard of is the batch normalization and the layer normalization. So the layer normalization, you probably, when you are seeing, if you pay attention, you really study the attention structure, you know, that the transformer architecture, you know, you have the attention, you have this layer normalization and the add and all that. So that's what it is. So what the normalization does, so for example, for batch normalization, so basically, you know, for this whole batch, we are going to basically shift the distribution of all these data. For layer normalization, we are just grouping all this data in this layer and do the normalization for this batch of the data. Okay, and we can also have, you know, instant normalization and group normalization. It's just like we are doing the normalization over a different set of the data. And then finally, talk about the activation function. So the activation function usually non-linear function. So most of the things that we've been using is the ReLU, right? So sigmoid and the ReLU probably is the most useful function we have learned. But why do we need a non-linear function like this? Like the ReLU essentially is the maximum of 0 and x, right? Why do we need it? Have you ever thought about this? Let's say like if we don't have this, what will happen? If we do not have ReLU, this kind of non-linear function, what will happen to the network? So far, for the network, we have learned so far, only has fully connected layer, convolutional layer, right? And we know the fully connected layer and convolutional layer, they are just matrix multiplications. They are all linear function, right? They're all linear function. And if we do not have all these nonlinear functions in between all these layers, this whole network is going to be reduced to one huge linear function, right? And the linear function just not powerful enough to do all these complicated tasks, all this classification, all this. By adding all this nonlinearity, just be more powerful to capture, to do all these complicated tasks. Okay. So when you ask why we need it, then we just need to answer like, if we don't have it, what will happen, right? So the expressive power of the network will be just reduced to one huge linear function. So that's that. Oh, so this is the transformer. This is like most of the large language models are using nowadays. This is just a very high level of the architecture. We are going to go into all these details of this whole architecture later. We're going to spend like probably 1 or 2 weeks to even just talk about this whole image. But give you a very quick high overview because like ChatGPT and all that, like the core is here. What it does is that you have this inputs, you have this outputs. Remember why we have inputs and outputs. Let's look at the inputs and the output. This is the input, this is the output. But for the input, why we have input embedding and output embedding? Anyone can answer? So think about like, at the very beginning of this class, I talk about how the models are doing autoregressive. So what autoregressive means that, well, once I have the input, I'm going to generate one token, right? Right. But next step, I'm going to use the output feedback as the next stage of the output, right? Combining with the new input. Does that make sense? So I'm going to do that to generate a new output, right? So that's that. So therefore, like we can divide this whole network into left and the right. Okay. So on the left-hand side, we have the input embedding, the positioning encoding. I'm also going to talk about that. We have this multi-head attention add and normalization. This is the layer normalization I just mentioned. And then we have this feed forward. Essentially, it's a fully connected layer, and the adding is kind of the skipping here, adding with this and normalization. And then this one feeds to this multi-head attention, and the output have this attention head and to this attention head. Initially, if you just look at the image, it looks like very randomly designed, right? But there's a reason that how it's designed. The idea is this. The very high level idea is this. Well, so now I have the input and I have all these output generated previously, right? I have all this older token already generated by myself, by this whole model. What happens is that this input is going to do so-called like cross attention with all these previous generated output. What that means is that, well, now I have already output some of the token. I have A. Okay, I've already output 3 tokens. I have A. And then like, well, give the new token and the older token I generated, what should I generate, basically? So I need to do the cross attention with the new input and the output to see, oh, with what I already out. Because if you think about it, when I have A, or like I like something, like all the older tokens I generate matters for what I generate for the next token to generate, right? So I need to do this so-called like this older token, the old output, and the new input, do the cross attention, and then doing the feed forward, and do the add and normalization, and do the softmax to give you the output probability. Right? That's kind of the main idea. And then if you look into this mask multi-head attention, and then you have this scale the dot product attention, this attention mechanism, this KV and the Q, and we all going to talk about this. In the center of it is this equation that you are doing the softmax for the query and the key multiplication, and times v. It looks very random, but after we unroll this whole concept, it will gradually just make a lot of sense how it's designed logically, not randomly, how this attention is designed. Okay, so now we just introduce all these basic blocks of the network. See how we are pieced them together to form all these popular networks we have seen so far, like AlexNet. You have this input image, then you have a convolutional layer, you have a max pooling, convolution layer, max pooling, convolution, max pooling, and all this linear or this fully connect layer. See, so that's pretty much just all the blocks we have seen so far, right? So so that's that, and that's give you all these parameters for each layer. Okay. VGG, also you can see that how it's have similar number of, well, a little bit more layers as than AlexNet, but it's pretty much just a bunch of convolution layer, max pooling, convolution, max pooling, plus the fully connect layers. Okay. ResNet. So one big thing about the ResNet is this residual connection. So this is skipping layers, right? So well, first let's look at this. So it has this convolution, max pooling, then this bottleneck block, and then let's zoom into this bottleneck block, the green block and the blue block. So for the green block, again, inside the green block, convolution, batch normalization, ReLU, convolution, batch normal. So it's all the blocks we have learned so far, plus this skipping idea. So this original input is going to concatenate with this, go through the ReLU and this. So the blue bottleneck is also like pretty much everything we've learned so far and doing this. And this one just shows like how the feature map actually going through, when the feature map going through the inputs, how the feature map actually shrinks and expands. Okay. So you can like, if you are interested, you can see like when you are using a 3x3 convolution layer, is going to shrink the output feature map, right? So remember, if you have a 5x5 convolute with 3x3, that's going to reduce to a 3x3, right? So 1, 2, 3, yes, right? So that's how it's shrinking the feature map and expanding it, and all that. So this is a MobileNet v2, very similar to this ResNet. Okay, so let's just give you some comment. And here I did not talk about the transformer, but transformer pretty much is a bunch of, no, we already have the transformer. It's just connect all these layers, give you this this whole GPT. So who know like what's the full name for GPT? You've been using it all the time. What's the name of GPT? G is what?
General purpose transformer?
Not general purpose. Generative. What is P? Pre-trained. What is T? Transformer. Okay, so it's a generative pre-trained transformer. And the core is that transformer architecture. Now we have about 20 minutes. I'm going to talk about like all these efficient metrics. We are going to evaluate whatever techniques we are designing. So well, we want the model to be smaller, faster, and greener. We want everything. So faster, we indicate like latency, right? So energy, greener means like the energy consumption. Smaller, we want like, that's a storage term. Core of it is the computation and the memory. So let's first talk about the latency, okay? So latency means that, well, when you start the inference, how fast you can get the output. High latency, 630 80 milliseconds to 46 milliseconds. So once you do the pruning and all these optimization, one of the goal is definitely going to reduce the improve the speed, reduce the latency. Throughput is another thing. Throughput is basically 1 per second, how many input you can process, right? So throughput and the latency are two different concepts. So question, does the higher throughput translate to lower latency? Does the higher throughput translate to lower latency? Yes? No? So let me give you this example. Well, the answer is no. Let me give you this example. So like in this system design, this system, for each input, I can only process one input at a time, okay? But for each input, I only need 50 milliseconds to finish the inference, okay? So now apparently for 1 second, I can process 20 images, right? But for each image, for each particular image, I'll only need 50 milliseconds to finish the process, okay? For this system, I can process 4 images at the same time. The throughput is higher. But each image takes like 100 milliseconds, okay? So that means that for 100 milliseconds, I can process 4 images, right? So for 1 second, I'm going to process 40 images. Does that make sense? So therefore, the throughput, apparently this one is higher. Okay, but the latency, this actually is worse because for each particular input, the latency is 100 milliseconds, and this one is only 50. Okay, throughput and latency, there are two different metrics. Well, this one kind of gives you an idea of how to calculate the latency. Latency equals the maximum of computation and the memory access. The computation equals the number of operations divided by number of operations process can process. The memory latency equals the data movement for the activation, the data movement for the wait. Okay, the data movement of the wait equals to the model size divided by the memory bandwidth of the processor of the activation equals to the input activation size plus output activation size divided by the memory bandwidth. So these are all different concepts. And when we are doing the optimization, when, for example, your goal is to reduce the latency, you need to compare the latency for the computation and the memory movement. And then you need to gradually chase down all the way down to what is the bottleneck of the system. Okay. And then you optimize. Well, the goal is that you just find the spot that's the bottleneck and you optimize that particular part, give you the most significant whole system performance improvement. Right? You don't need to be good at everything. You just always when we are doing the optimization, we always find the current bottleneck. Energy consumption. So the data movement means the more memory reference means more energy. So the energy consumption, you can see that for data movement from the DRAM, it's significantly higher than a computation. Okay, that's almost 200 times higher. So the takeaway is that, well, if you can do more, so here, I can do 200. Well, for add is actually even more. For multiplication is 200 times. For adding, it's 6,000 times higher. Okay. So the takeaway is that a lot of times, if you can compute more and get less memory access, do it. Okay. So it's all about the cost. So we talk about latency, we talk about the energy. Let's talk about the storage. So first, we always heard about the number of parameters for a model. The number of parameters is a parameter like the weight of the given neural network. So this one kind of gives you how to calculate number of parameters. So I give you all these information, right? For for the linear layer, what's the parameter size for the convolution layer, for the group convolution, for the depth-wise convolution. That's kind of how you calculate the number of parameters for all these for all those parameters. So let's put that into action. So for example, like AlexNet, okay? So for AlexNet, for example, for the image, it's a 3 is the channel, right? RGB. And the image dimension is only 224 by 224. So that's a very low resolution image, okay? But 3 channels. And then you go through the convolution image. I'm sorry, go through the convolutional layer. This layer has 64 channels. You have the stride. We didn't talk about stride, but do you guys understand what is a stride? So when you are doing the convolution, in the previous example, the convolution, the filter always move to the next cell, right? You're just sliding through this, right? It never jumps, right? So the stride basically says you can jump. Like now, when I'm doing the convolution for this window, and I don't need to move the immediately next window, I can actually jump to a couple of steps. Does that make sense? So that jump is the stride. So that's the stride size, this pad size, and that pretty much gives you how much weight you need for this convolutional layer. Make sense? Okay. And the same for the pooling, for the convolution. So that's with all these calculation, you kind of have all these, okay? And then you just, add them together, and that gives you the total 61 million parameters in total. Okay, and that's just a number of parameters. And assume if you are using a 32 floating point number, each floating point number is 4 bytes, right? So 4 times this, that's 244 kind of megabytes that you need to store all these weights. So one of the early applications for AlexNet is actually this. They were actually designing this for the bank. You know why they need this? Yes.
To approve loans?
No, it's image recognition, right? It's image recognition. It's for the ATM machine. So when you deposit the check, it's recognizing the routing number and the account number. So therefore, like the image resolution is not that important because the image is small anyway. It's not like a high resolution image. And there are a couple of other things that we need to be aware of. So the number of activations is different from the number of weights. The number of weights is like the model needs to be stored in the memory. The activation is that when you are running it, the input going to do the multiplication with the weight, right? Doing all these multiplication addition with the weight, and they're going to generate this intermediate results. So those are the activations. Does that make sense? And that size is different from the weight. So see, this is the parameter for ResNet 18 and the MobileNet v2. Okay, but the activation is this. They are 2 different things. So apparently for these 2 networks, ResNet 18 and the MobileNet v2, the parameter is the one. Once you have enough space for the parameter, you pretty much have enough space for the activation. Activation is relatively negligible compared to the weight, right? But the activation distribution actually is quite different. What that means is that for all these different blocks, the peak memory is very different. It's not balanced. What that means is that in some of the blocks you need such a big memory to host all these activations, but some of this you do not need. why is that a problem? The problem is that if that's the case, it means that you need to have a memory that can host all these activations, right? But for the majority of the time, all those memory spaces are wasted because they are not used. Right? So that means that like if you can do some optimization to kind of like balance all this memory usage, you can essentially reduce the required memory to run this model. Does that make sense? Yes.
What do you mean when you say activation? Is that like the ReLU activation function being positive?
The activation means for each layer, let's just look at the layer. You have the input coming in, right? This layer has all these weights, right? And then you are going through all this convolution and blah blah, and you are eventually going to the ReLU and give you the output, right? The whole thing, let's call this, because the activation, in order to generate the activation output, you need to go through all this thing, right? So the activation means the whole computation. So you need the memory to store the input, the memory to store the output, and the memory to store the weight. Does that make sense? Well, of course, like we all learned computer architecture, we know that you can have caching, you can have memory swapping, but that's not what we want, right? Because the memory swapping, we already know that the memory swapping, the caching is going to take extra time to do the memory swapping. So if you can have the memory to have everything for this whole layer of activation, that's ideal. So the activation is the memory bottleneck in training, not the parameter. Right. So we are also going to talk about the training. So if during the training, this is during the inference. So this is during the inference. The parameter, the weight's going to take much of the memory space. The activation is relatively small. But during the training, the activation actually is going to take much more memory than the parameter. Okay, so that's why activation, the training needs much more memory. This is the activation of weight memory distribution of a MCU net. It's like a network designed for microcontrollers. And you can also see that the activation requirement and the weight requirement are kind of different. In the earlier layers, the weight only needs a small amount of memory, but the activation needs quite a big memory. During the lower layers, the latter layers, the weight needs a lot of memory, but activation requires less. So all these characteristics, when we are doing all this profiling to look into the usage of the memory, the point is that like we want to look at them like what it looks like and what are the optimization, what are the bottleneck, what are the optimization opportunities are there presented here we need to do to make the system smoother. So this is the activation calculation for the AlexNet. Okay. Oh, and finally, we talk about the Mac. This a Mac. It's not the MacBook. It's this accumulate operations called one Mac. So this multiply and accumulate. Okay, that's one Mac. Also, we have this matrix and the vector multiplication. We have the general matrix multiplication, because these are all these very common operations inside of all these networks. So what is this? So this calculates the MAC operation for all these different layers: linear layer, convolution layer. So that's just give you different kind of. You guys can actually go verify all these calculations. Basically says like for this layer, how many max you're gonna need to finish the whole calculation. So that's how much calculation we need for AlexNet. But remember, one Mac has two operations actually, because one multiplication, one accumulation. So one multiply plus one add, right? So this is the Mac operation. So if you want to calculate the operations you need to multiply this by 2. Does that make sense? also like another term you often see this flop. So it's a floating point operations, right? So AlexNet has this 724 million max. And because each MAC has 2 operations, and if you, without quantization, each MAC basically has 2 floating point operations. So that's going to be 1.4 giga of flops. That's how much you need to run one inference of AlexNet. That's that. So wow. So hopefully by now I convince you that wow, today's AI is powerful, but it's big. Efficiency is very important in terms of a lot of speed, memory, and energy, and eventually like the money you cost in both training the network as well as serving the inference. It's too big. And how should we make the deep learning more efficient? All right. So that's kind of the summary of today's class. And we are going to talk about all those optimizations one by one. All right. So that's all for today's lecture.